So, hello everyone. Uh, Today I want to discuss this important topic of phasors, but from a very different perspective, which I believe is important as a 2020 vision. There is a lot of confusion about uh, what the phasor actually means. So you will see lots and lots of tutorials about how to use phasors. Every engineer knows how to use phasors, but what it means, and sometimes the meaning is more important if you want to apply it to all kinds of problems. So let's start by asking these questions. Why should we bother? So everyone knows that phasors are complex numbers. So because you associate complex numbers with complications, so why should we complicate things? And what is the real deal? Okay, actually what is going on behind the scene? And can we replace these phasors with reals? Yeah. So what is simple and what is complex? So what do we gain by using complex numbers instead of reals? So let's try to answer these questions. So the lessons which you should learn from arithmetic, from real arithmetic, are two lessons. Yeah? That you should see addition as a translation. Yeah. So to know, let's say you start from A and you add B to it, you get C. So you want to know what changed as you went from A to C because you added B to it. What changed? So that can be understood by looking at 0, yeah, in relationship to 0. So actually the difference between where you started, which is A, and where you ended, which is C, that is the same as the difference between 0 and what you added. So 0 is important for addition. Yeah, actually you are changing 0 by adding things. And multiplication is a different game. Yeah, it's called scaling, and it changes 1. Yeah, so if you start from A again and you go to C by multiplying B, and you want to know what is the difference between A, where you started, and C, where you ended, as a result of this multiplication, that difference is actually a difference between B and 1. So you want to know what happened to 1. Remember this. In addition, you want to know what happened to 0, and in multiplication you understand this by trying to answer what happened to 1. We will use these two principles for developing basically the idea of complex numbers. We would like complex numbers to behave in the same way. Yeah. So complex numbers is nothing more than laying down two axes. You have one real line, let's say the x-axis, and another real line, the y-axis. Yeah. So instead of points on one real line, because on this real line you can have points, yeah, so real arithmetic. On this real line you can have points, real arithmetics. But if you want to remain on one of these lines, you can only do real arithmetic. For complex arithmetic, you have to think about points in this plane. Yeah. So even this point has to be seen as a pair of points. So every point has to be seen as a pair of numbers. Yeah. One number on this x-axis and one number on that x-axis. So if this is x and this is y, these two combined will give you 1 point on the x-axis in this xy plane. So we want to know how do we add in this plane. So for example, if I have 1 point here, and if I have 1 point here, so let's say this is x1 y1 and this is x2 y2. How do I add these two lines, these 2 points? Yeah, so I can learn from real. Addition must be translation. So if I want to know a third complex number, which is a point, I want to know what should I mean by the addition of these two. I'm adding one complex number to another complex number, actually 1 point to another point, and I get a third point. Yeah, so this actually I translated from 0. I started from 0 0. 0 is different now, and this complex plane 0 comma 0 will be my 0, and you changed this. So what happened to this? You started here, yeah, and you ended here. This was your end point. The difference between the start and the end is actually the difference between 0 and what you added. This dictates the rule of addition. So addition is not arbitrary, it must behave like real numbers. We will derive similar rule for complex numbers. So in complex plane we can again start with 1 point. So let's say I have 1 point x1 y1, and I have another point x2 y2, and I multiply these two, and I yet don't know what multiplication should look like, but I am looking for it. So multiplying this point by this point should give me a third point, and that, because it's multiplication, it should be changing 1. You are changing 1 by multiplication. So the difference between this start and this end, you started at 1, you ended at 3, should be the same as the difference from, so here 1 0 is your identity. Yeah, this is your 1 0. What happened to 1 0 is important. And remember, here you write the point which changed 1. So actually it is not very convenient to use this x and y. You must know that you can replace these with polar coordinates, and in polar coordinates this 1 0 becomes cosine 0 sine 0, x2 y2 is cosine theta 2 sine theta 2, r2 is the magnitude, and so on for others. And if you carefully look, what happened here is that the difference between these two must be the same as the difference between these two, and that means that r3 divided by r1 must be equal to r2, and that gives you the rule of multiplication for the magnitudes. But something very different happened to angles. Yeah, I don't know how do I go from theta 1 to theta 3, yeah, whether it's multiplication or addition, but here I know I went from 0 to theta 2. So to go from 0 to theta 2, you cannot multiply, you have to add. So basically you started from 0 and you added theta 2, so it's addition. So the same is there. That theta 2 is actually added to this theta 1. Yeah, that same, if it can add to 0, it can add to theta 1 as well, and that gives you theta 3. That's the rule of multiplication in complex numbers. It has to be this way, there is no other way. Yeah. So to recap, addition is again translation, but this time it's in 2D, and multiplication is not only scaling, because in real it was only scaling, but now it also involves rotation because the angles change. Yeah. So multiplication in complex plane is rotation as well as scaling. It involves two operations, and translation is simple translation. So let's see how we use these ideas. We are now into the actual problem. So say what impedance and the whole idea of phasor revolves around around impedance. We need something like resistance. So what you need to know is that the impedance, this is a new concept, it will generalize resistance. Why is resistance limited? For example, if I have a simple resistance, I can easily link current and voltage by a simple law. Yeah. So V equals Ri, algebraic relationship. R multiplies, so scaling, and I equals V over R. Yeah, this is simple scaling. So R basically scales I, or 1 over R scales V. Now if I need something like that for other elements like inductor or capacitor or a combination of those, I will not get this simple scaling, because you have integration, you have differentiation, you have a combination of integration and differentiation. Things get messy. So we should not expect simple rules. So let me now actually start this. Let's say I have a general circuit. I don't know what is inside. Yeah, there are many complicated things. And let's say I apply some voltage to this V, and somewhere in the circuits there is some current, and I want to relate these two. Yeah. Now if this is a linear and time invariant circuit, you know what I mean by that. All the parameters, all the resistors, inductors, capacitors, all the things, they don't change with time. So if that is the case, then you can show from basic trigonometry that if this voltage is a sinusoid, yeah, it can start at any point. I mean, actually it starts, it is an everlasting sinusoid, but where you define your zero could be here, it could be here. So wherever you define your zero, that will change this initial phase. So let's say initially the phase is theta V, and this is your voltage, this is the peak value, and let's say this is a cosine with frequency omega. So you can show that, okay, because everything is linear and time invariant, the current anywhere in this circuit will have some magnitude which will be related to that magnitude, and it will also be a sinusoid with a different phase. So actually what happened, that the sinusoid didn't change, the frequency in particular didn't change, it's omega, only the angle changed, and the magnitude also changed, the peak value also changed. So two things. Yeah, if it were only a resistor, then this would not change. Yeah, so if it were a resistor, this theta V, this would also be theta V, but in general the angle will also change. Now this is something which you already know, I don't need to educate you on that. Yeah, so let's get to the main point which is bothering me, and it should also bother you. So you know, let's imagine you started with a circuit and you solved it. You started with a voltage sinusoidal with some angle, some phase, and then you calculated the current, which is another sine wave with another phase and another peak. So I am trying something like that. Can I relate these two quantities and write something like resistor here? If I try that, I will have a problem. Let's try that. So I will have Vm cosine of something, Im cosine of something. Now because this cosine and this cosine, they have different arguments, they cannot cancel, and I do not have a simple relationship. Yeah, this thing depends on time, because this is time, this is time. I do not want a ratio which depends on time, because that will be a useless ratio. Yeah, previously if you compare it with resistor, when we tried something like that, V over I for a resistor is simply R. This R does not depend on time, it does not depend on current, it does not depend on voltage. R is just R. So that is why it was so useful. We need something as useful as R for a more general setting, for AC. Basically this is an AC voltage. So one thing is very clear, that as long as we stick to real sinusoids, real AC waveforms, there is no way we can relate voltage and current in a simple way. And by simple I mean as simple as a resistor. So let's try something. Now you will see the magic of complex number. So let me now try something interesting. So in complex theory you have this plane, so you have one real line, so things happening on this real line, things happening on this real line. Let's say I have that circuit which I showed to you here. So here I applied V and I am interested in some current, and all the arithmetic, all the calculation will be done on this real line, because all real numbers, all voltages, all currents, all resistors, everything will be on this real line, and I call it the real line. Let's imagine another line, which is also real, but because these are two, so people call it imaginary line. Actually it's also real, it's as real as this real line. So let's say you have another real line, and you imagine an exact identical copy of this circuit. All the resistors are the same, all the inductors are the same, all the network, everything. Actually you duplicate this. Conceptually you just have a duplicate, or you just imagine it, you imagine the same thing, and you do not apply that same V, you apply something called the orthogonal V. This perpendicular means that if this was sine, cosine, this must be sine. You see, nothing else changes, because the difference between cosine and sine is 90 degrees. That's why 90 degrees phase, introduce that 90 degrees of phase. If that were sine, this would be cosine. If that is cosine, this will be sine. So you just introduce, and that is also sensible because these two lines are also 90 degrees, so you have that correlation as well. Of course, because you changed, so you didn't change the circuit, you took the same circuit, you just applied a different voltage, which has a difference of 90 degrees of phase. So the current will also be different, it will also be I. So if this voltage differs from this voltage by 90 degree, this current will also differ from that current by 90 degree, and that's why I use this symbol. So if this is cosine, this will also be sine. Nothing else will change. So these two both are real equations. They correspond to, so remember, real voltage, real current, real circuit, real line for arithmetic, another real voltage, another real current, that same real circuit, another real line. And when you want to combine these two arithmetics, and you want to have a common arithmetic complex, then you call it imaginary and then you call it real, but that's only convention. In fact, they are both real. But what do we get out of this? So remember, if it was difficult for this equation to try something like this, if this was not easy, it is also difficult for this, that V orthogonal divided by I orthogonal will also be difficult. So they are difficult to deal with in isolation. But let's try to consider the pair of responses. So let's bring this I and this I orthogonal here as a point. So you will have a point I, and of course this point will change with time, but we don't, let's say we freeze time. And similarly you have another point V. So all these pairs of voltages, so I can now connect the pair of voltages, one voltage, the other voltage, they both apply to the same circuit but in a different setting. So I just take the pair, and this will be corresponded to a pair of currents. Now here is the magic of complex numbers. Because these angles add, theta v added to omega t and theta I is added to omega t, and we know from complex analysis in the previous slide that angles only add when some complex numbers are multiplied, which means that this must be seen as a multiplication of complex numbers. It means that you can rewrite this pair of voltage as if you have one complex number. Remember, this does not include time, it only includes the initial phase of the voltage, and you multiply this by a time dependent complex number. So you break this down to two factors, a time free or time independent or a constant factor and a time dependent factor. They are both complex numbers. You multiply them and you get this complex number, a pair of voltages. The same you do with this pair of currents, a time independent or a constant complex number and a time dependent complex number. Remember, you see the time dependent part is the same in both cases. Now because this time dependent part is the same, it is a complex number. It is a complex number. If you now try this ratio, so now try to divide this complex pair of voltages by this complex pair of currents, that will cancel out. It was actually bothering you on the real line. On the real line, a cosine will never cancel with a sine, or a cosine of one angle with one phase will never cancel with a cosine of another phase. But here they just disappeared. And now even though you have these cosines and sine, they will not cancel, but now there is no time dependence. It is constant. So you have a constant time invariant relationship between the pair of voltages and the pair of currents. This was only auxiliary. Let's say you complete this mathematics, so you will have a real part and you will have imaginary part, and this is what you mean by impedance. So the impedance is the ratio of two pairs of quantities, a voltage pair and a current pair, and without this additional current and additional voltage, and remember you are not adding, you just take the pair, yeah, although you write this like this, but this is not an addition. You don't think that you have one voltage source in series with another. There are many stupid authors actually who think of it this way, and they write a J with it, but writing J will not solve the problem because J is an operator, J is not a number. Yeah, so this is actually not a very good way. You should think of it as a pair, and you should think of it this way. Yeah, you think of two copies of the same circuit, each one of them is applied different voltage. Do not try to put these two voltages in series because that is stupid. That doesn't make any sense. You have two real voltages and you try to add them and you will get something different. Similarly, the pair of current divided by the pair of voltage, you do all that math, so this will be admittance. Yeah. Now we actually we are done, but let me just tell you one more thing. So it appears that you only have this is called a phasor because it only depends on the phase. Yeah. So impedance is basically a phasor, admittance is a phasor. So why do we need current phasor and voltage phasor? Actually, when you divided this pair of voltage by this pair of current, we know the time dependence is common, so we should not bother about writing that time dependence every time. So actually this quantity, although this is not the voltage, this is just the constant factor in the voltage, but we should not bother by the time dependent factor, and this is what I mean by the voltage phasor, and this is what I mean by the current phasor. So what do I mean by voltage and current phasors? I know I have a pair of voltage and a pair of current. The pair of voltage has been factored into a constant complex number and a time dependent complex number. You disregard the time dependent complex number because you know it will always be there, and the factor which is constant, that is what I mean by the voltage phasor. So voltage phasor is not equal to voltage for two reasons. One, it is a complex number. The other, it does not include time dependence. So when people say it is a rotating vector, that is also misleading, because rotation is a consequence of this time dependence, and when you disregard the time dependence, then you should not be calling it a rotating vector. So that is also actually a misunderstanding of the concept. Yeah, and then you can do some nice stuff. You can multiply voltages, and you see these active power and reactive power, they're also real powers. They only differ. I mean, we discussed this in some other video. Yeah, there is some other subtlety which I don't want to get into. This I wanted to keep this video short. So thank you. That was it from my side, and stay safe and stay healthy.